Hello, and welcome to the world of physics. Today, we'll be talking about toilet paper rolls. Well, technically falling toilet paper rolls. So, the question is, what is the ratio of heights of two toilet paper rolls, one held at the free end, and one simply dropped, needed to ensure that they hit the ground at the same time? What does this mean? Well, I'll be simply dropping one toilet paper roll and let gravity do all the work with one of the trials, and the other trial will be with me holding the free end of the toilet paper roll and letting it unroll while falling. And the entire task is to find a ratio of height so that they hit the ground at the same time. Before answering this question, let's ask another question. What happens when we release them from the same height? Well, let's see. Alright, so what happened there? Well, clearly the one that was simply dropped hit the ground first. But why was that? That's because that one had only linear motion. So it had to convert the gravitational potential energy only into linear velocity. However, the one being unrolled had angular motion plus linear motion. This is because it was unrolling. So it had to convert the energy it initially had into angular energy and linear energy. So now for the real question. What is the ratio of heights necessary so that they hit the ground at the same time? To derive the expression for the ratio of height, we need to know a few things. First of all, we'll have to know the center of mass of the hollow cylinder when we're deriving the expression. We have to know about torque and how torque equals RF sine theta, which is equivalent to the product of the moment of inertia times the angular acceleration. We have to know about energy concepts, about something called the parallel axis theorem, and some simple kinematics. And now for the derivation.
Alright, so now it's time for the derivation, the messy part. I'm not just saying that because my handwriting's messy. Alright, so the first way we'll be deriving is using net torque with the central axis at the center of the toilet paper roll. From here, we can see that the force of tension is the only one causing a net torque on this rolling object. Therefore, Ft times R2 is equal to the moment of inertia of the toilet paper roll times the angular acceleration. From this diagram here, we can see that Ft minus mg equals m times negative a, or that Ft equals mg minus ma. Now, we know that A is equal to A over R, and that I of this object here is equal to half m times R1 squared plus R2 squared. Plugging this back into this equation, we get that m g minus a R2 equals half m R1 squared plus R2 squared times A over R2. Solving for acceleration, we get that A equals 2 R2 squared over R1 squared plus 3 R2 squared times G. Now we use kinematics for the object that is not rolling and falling, which is the still toilet paper roll. We can get that h equals half gt squared, as the acceleration of the falling object with no rotational motion is just g. And we'll call that h2. h1, this falling object right here, it can be described by half at squared, using the acceleration we get here. h1 over h2 equals a over g. The halves and the t squareds cancel out. Now plugging this into that, we get that h1 over h2 equals 2r2 squared over r1 squared plus 3r2 squared. And we have derived the equation for the ratio of heights between a rolling object that's falling and a normal object that's falling. Okay, now there's another way to derive this too, using an axis of rotation other than the center of mass. In this derivation, the axis of rotation is the point of contact between the unrolling toilet paper roll and the toilet paper roll itself. The parallel axis theorem states that the moment of inertia of the parallel axis is equal to the moment of inertia of the center of mass plus the mass of the object falling or rolling times the distance from the center of the axis of rotation squared, which in this case is r2, as you can see here. Therefore, using the net torque equation, Fg r2 equals I of parallel axis times angular acceleration. We see this because the force of gravity is the only force causing torque, as the force of tension is at the axis of rotation. Therefore, mg r2 equals half m r1 squared plus r2 squared plus m r2 squared all times a over r2. Rearranging this for acceleration, we get that a equals 2 r2 squared over r1 squared plus 3 r2 squared times g. Going back to kinematics equations, h2, the height of the normal falling object is half gt squared. h1, the height of the rolling falling object is half at squared. And h1 over h2 equals a over g. Plugging this into that, we get that h1 over h2 equals 2 r2 squared over r1 squared plus 3 r2 squared.
Alright, so now we have an equation that tells us the ratio of the two heights. So, what now? Well, now it's time to try it. Let's go back to that equation. It states that the height of the rolling object over the height of the normally falling object should be at a ratio of 2r2 squared over r1 squared plus 3r2 squared. Using values I measured of the toilet paper roll, with r1 equal 2 centimeters and r2 equaling 6 centimeters, this equation yields that the ratio of the height of the rolling object to the height of the normal object should be approximately 0.643, or about 2/3. Now, the height I'll be dropping the normal object from is 231 centimeters. You can see, and using that equation with the ratio of 0.643, that yields that I need to drop the rolling object from a height of 149 centimeters. Alright, now what you've all been waiting for, the drop.
5, 4, 3, 2, 1, 0.
Alright, it worked. I guess physics does work sometimes. Now I'll be discussing sources of error and assumptions that I made in the derivations. Firstly, I neglected air resistance completely. Air resistance would have provided frictional torque, which would have changed the derivations a bit. Then, I did not account for the fact that the radius of the roll that was unrolling was changing as it got lower and lower. This would have made a significant difference. Then there were errors in measurement, errors in drop time, and a human error in handshaking. Also, the mass of the second object that was falling was changing, and this wouldn't have changed the rate of falling, but it would have changed the air resistance. Also, when released initially, both of the objects may have been at an angle, so the forces acting of them would have been slightly different. And finally, the top object, when it dropped, usually it got a tiny spin in the other direction, in the z direction. In conclusion, this experiment should have shown us that rolling objects fall with less acceleration than normal objects due to the rolling moment of inertia differing from a normal particle's inertia. Also, we should have learned that the rolling motion of any object can be tracked around any axis. And that's about it. That was fun. That was great. And I would like to thank everyone who helped me. Bye bye. Good night.